that get turned into a computer? Like, what is it? What's the part of the computer you're replacing?
I mean, sort of fundamentally, it changes everything. It changes the very concept of computing as we know it. So,
Okay.
I mean, the nice comparison is all computers are based on binary. They're all like ones and zeros. And quantum is just a whole new sort of paradigm, a whole new way of programming, a whole new way of building a computer that doesn't rely on ones and zeros. So it doesn't use existing programming methods. It doesn't run doesn't run Excel, doesn't run Microsoft. It's a completely different way of looking at a computer because it's not based on ones and zeros. It's not based on like how all other computers are built. It's like a fundamental rethink about how you build a computer.
And why? What is the fundamental change you're getting here? Because ones and zeros are sequential, so everything has to happen in a logical sequential timeline. But in a quantum computer, things can happen at the same time.
Yeah, that's right. So trying to just describe it, like normal computer, I don't know, you're trying to add up two numbers. So you got a 1 plus a 0, gives you 1. That's sort of one thing you can do with 2 bits of a normal computer. With a quantum computer, you can still do that. You can still have a quantum 1 and you can still have a quantum 0. But you can also have one qubit being like 50% 1, 50% 0. And the second qubit, the second bit of information being 25% 1 and 0, and 75% 0. So it gives you like another sort of parameter,
It's almost like another dimension of it.
Yeah, that's probably the best way to look at it. It's just it gives you an extra sort of dimension of your data. So it makes every bit, it gives every bit in your system more combinations of what's possible. So you've got 2 bits. I'm going to fail doing this. There's like four ways you can arrange 2 bits. With a quantum computer, there's still 4. But as the number grows, the number of different ways you can arrange 2, 3, 4 qubits is much greater than the number of ways you can arrange 2, 3, 4 bits. I keep getting distracted by the physics side of things.
Yeah.
I just try to describe it. It's just completely. You shouldn't really look at a quantum computer and say, well, how does it compare with a normal computer? It doesn't really replace a normal computer. It's sort of something completely different. I mean, back to our sort of customers we work with to try and look at this stuff, we spend half of our time asking them to come up with things that they had tried to do with a normal computer, but just forgotten a long, long time ago because it was just nowhere near possible.
Will there be a time in the future where our personal computers will be quantum computers?
I don't think so.
Because this is a hack for specific goals that you want to achieve.
Yeah. So
you found a way of creating things that you can process and solve problems in a different way.
That's right. Yeah, and maybe if any of your audience are into sort of hardware, probably not many of them are, but there's sort of GPUs which sort of started life. If you're a sort of gamer, like GPUs started life because it helps you like run computer simulations, helps you render 3D objects. Mm-hmm. But people worked out that these like really specific like pieces of hardware were quite good for
mining cryptocurrency,
like, and sort of doing one very specific operation, which is sort of multiplying matrices, and now that sort of spawned a whole like NVIDIA sort of, I forget what they are, like $200 billion company, just selling hardware that just does one thing really, really well. Like,
are you building a quantum ASIC?
No, we are not.
Can we talk after the show? I've got an idea. I've got a way of making us a lot of money. Have you looked into this? Because that is one specific task.
Yeah, it's really interesting. I guess on that side of things. So I mean, most quantum hardware isn't. We use ASICs to drive our hardware, but it's not the quantum hardware we use because the hardware we use is just so completely different from everything that exists currently. It's different. What's sort of cool about this space is that basically everyone's looking again at how you solve sort of computing sort of problems, and like because they're looking at things how you do it with a quantum machine. They're just looking at how you might do it completely differently, and it comes up with like loads of. In fact, Fujitsu have got a really cool project working with ASICs. It's not quantum at all, but sort of they spent a bit of time looking at quantum, and they learned a new way to drive ASICs.
Are we talking about different things with ASICs? Are you talking about
Possibly.
Generalized ASICs? I'm talking about Bitcoin mining ASICs.
I'm talking about generalized ASIC.
So another thing I learned today: ASIC is not a Bitcoin term; it is a computer.
Did you not know that?
No, I didn't know that.
Oh, okay.
It's application specific.
Yeah.
Yeah, I guess, I mean, it's kind of obvious, but no. So we have ASIC miners. Grab one up. And have you ever seen one of these ASIC miners? There's a company like Bitmain. They produce them. They're up to like an S19 is their latest machine. And they have one job. Okay. So their job is to mine Bitcoin. And they keep running essentially it's a random number generator, essentially, to try and find the specific hash to find the Bitcoin. I say it like an idiot. But that's all they do.
Awesome.
And they try and do gazillions of attempts over and over and over. And once one finds it, a block gets found, and then we move on to the next block in the blockchain. Can you build one of these for me, and how much? And when can I have it?
So I tell you what we would do.
Exclusive rights.
I tell you what we would do. If you were a customer of us or any of the other quantum computing companies, we'd take a look at the problem you're trying to solve, like which is mining Bitcoin and what that looks like, and we would try and design our own quantum ASIC to sort of solve that problem, taking advantage of all the quantum stuff. We design a quantum program that helps you look at whether you can mine Bitcoin faster, more efficiently.
So based on what I've just told you, there is enough there for you to go, this is something we could look at.
Maybe, yeah. I mean, I don't know.
But the price of one of these is what, like 15 grand?
Well, even less now, like $5,000 in the market.
Oh, there you go.
Yeah, but if the quantum's so good, you might only need one. So,
I mean, if anyone was serious about this, what we would do is we'd get a team. So we have a team of really excellent quantum people who are also sort of pretty good on the machine learning or whatever side, and we give them that problem, and it takes probably about 3 months to just have a first look see to work out if there's anything there. So imagine we're trying to,
I am serious. How much? So what do you charge for? No, I mean, I've got a feeling you might have people reaching out to you after this. And do you charge people for that 3-month research?
It depends. I mean, we're trying to run a business. So, you can imagine what it's like. We try and work out, how strategic do we think this is? How likely is it that it will lead to something that's going to help us sell hardware and run a business? And we take a judgment on that. So, yeah.
Huh. What do you think, Danny?
I mean, is it something that can like work alongside like a traditional, like could you have a quantum element of like a Bitcoin mining ASIC?
Yeah. So, I mean, what I will say is I'm probably sure if there are any quantum people listening in the room, they might be screaming at me being like, it's not possible.
They'll be screaming at us, don't worry.
Right. I mean, somebody already must have looked at this anyway.
Yeah, I'm sure.
People probably have, yeah. But the field is changing all the time. People are learning a lot more every day about what can be done, what's possible and what's not possible with machines today. Not possible.
You created a new word. Actually, quite
efficiencies.
Yeah.
So you don't know. And, I'm pretty excited about, but back to your point, the sort of route to try and do something with these machines in the short term, bearing in mind, you've only got the best machine's got 100 qubits, is to combine it with what you're trying to do already. So just imagine sort of palming off very small parts of your problem to a quantum machine. But so maintaining the current ASIC, whatever you're trying to do normally, but just maybe your computer programmers have worked out that one very small part of that problem is really, really hard, or the sort of core of the problem that means that it takes longer than is your bottleneck. And what people sort of the state of the art in this industry is looking at, okay, if we put that in, we solve that particular small part of the problem on the quantum system, can you do it faster? So that's the holy grail. That's the sort of really exciting short-term race in quantum computing at the moment. Put high-end classical ASIC or whatever classical computer side by side with a quantum machine, allow them to pass information super fast between each other. Does that provide any benefit? And the answer so far, to be honest, has been no. So this stuff isn't providing any, but there are applications emerging that look sort of interesting enough that, and by the way, as soon as anyone shows this, as soon as someone says, okay, this is something that is possible in the short term, that's it. You're already on the way to demonstrating value with a quantum computer, which is...
If you solve this on the mining front, you present the risk then on being able to hack people's private keys, don't you? Because it's a similar-ish risk.
I mean, you're asking me. I think you're asking the wrong person.
Yeah. But then I guess it could just speed up mining, it could just give you an edge.
Yeah.
I mean, if the miners, they're essentially just spinning out numbers and trying to find the random one, which essentially allows them to unlock the block. And I don't know what that is, terahash per second they talk about, isn't it?
Yeah, I don't know what we're at the moment.
You know, it might be a case of if you were doing this, you just speed it up. So you can make an ASIC. You can, I don't know, you can add a like 10, 20, 30% edge to all the other ASICs, which probably wouldn't justify the cost.
Possibly. And this is the world that Quantum's in at the moment. So, and to be honest, a lot of our customers, the way it works best is if they throw at us loads of computational problems and we go, no, none of these are possible. Oh, that one looks possible. None of these are possible. Or they might be possible, but they'll take a machine which is much larger than we've got today.
Yeah.
And actually, to the point about decryption, that's something that everyone talks about quantum computing being useful for. That's actually not that the machines that are needed to break like RSA encryptions or even sort of your sort of hashing type problems. You need billions of qubits. So, you know, I've been talking about machines that have hundreds of qubits.
What's the one you've gone from 1 to 10? Does it go in factors of 10, or are you just constantly talking about that?
So that's currently the thing that's debated and researched the most at the moment. So sort of within Orca, I think within most companies, they're aiming at sort of breakthroughs that give you like a step change in the number of qubits that you might have. So everyone sort of knows that at the moment you're going from 1 qubit to 2 to 3 to, I don't know, 64 to 128. There's still a world away from billions of qubits or millions of qubits at the point where you're starting to solve some really juicy algorithms.
Going from 1 to 10, what is the complexity from getting from 1 to 10?
So, I mean, on that side, these things are all hard, but 1 to 10 is fairly straightforward. A lot of companies have done that now. Lots of different platforms have got to.
What did you solve to do that, though? Like, what is the complex problem that's being solved?
So for us, I mean, it all relates to the hardware, the machines we're building. For us, to be honest, we're just trying to make very high quality single photons. So what I talked about earlier, we're just trying to, for us, the reason why it's hard to get to 10, it's sort of related to how easy it is to make single photons. So it's sort of like that. It's like an engineering challenge. Just, can we make a single photon? Yes. Okay, can we scale that up to make 10 single photons at the same time? It's that type of problem.
And when you say at the same time, is it 10 different sources of photons, or is it one source creating 10 photons?
Yeah, 10 different sources of photons.
And are those 10 photons going around the same maze or a separate maze each?
So all of those photons will go through the same maze, but they'll all interfere with each other. They'll all overlap. So, you know, the problem, when I described it earlier, I talked about one photon can take lots of different paths through the same maze.
Yeah.
Imagine how much more complicated it can get if you then have 2 photons, and both of those photons can take every path through the maze. But every time that they overlap, every time they meet those 2 paths, something weird and quantum happens to make it even more complicated. And now imagine like 10 photons going through that same maze. Every one. Sorry if I've lost you.
No, I'm fine.
Every one of those photons can take every path through the maze, but every single time any of those photons meet, there's like an interaction. It changes. So all of those 10 photons are all interdependent with each other. And now imagine that you can program that system, and then that becomes the heart of a completely new type of building a computer, which is a quantum computer.
And how do they carry information, and how is information extracted from this?
Good question. You insert them into the system, so you've got a bit of information encoded in how and when you insert your single photons into this big maze system. You can change the maze, so it's a bit like, what's that movie, like Inception, I think it is, where they, really cheesy movie where they're like building mazes and things. Half of this job is to basically build, so the maze basically sort of in an abstract kind of way represents the calculation you're trying to do. I probably lost you now. So anyway, so that you can design the maze, you can change the maze, you can change the maze in real time. So, and that maze structure basically reflects the problem that you're trying to solve. And this is like deep maths I'm trying to describe now in a sort of...
Yeah.
And then what you basically do is you measure the outcome of the maze. So you can see where the photons appear. And at that point, you can measure them, which stops them being quantum. And all of a sudden, you can basically find out the very exotic and weird many paths that all of these photons have taken through the maze. And if that's completely lost you, I'll just say that represents a way to carry out a calculation. So you can make your maze look like, I don't know, a Bitcoin mining operation. You can make your maze sort of, and the outcome of the maze. So if you successfully navigate your way through the maze, it represents a correct solution to a mining piece of Bitcoin.
Huh. Okay. Yeah, I mean, I barely understand most of what you're saying, but at the same time, like, I think I'm taking a slight step forward. Okay, I think I understand a bit more. So therefore, to go to 100 qubits is a factor of 10 complication from 10.
Yeah.
And is it, sorry, I'm just trying to figure this out in my head. Can calculations go wrong? Because it seems like ones and zeros are pretty logical. It's binary. Because this isn't ones and zeros, can calculations go wrong?
Yes. Yeah. So actually, that's one of the major challenges of quantum computing. Because everything's basic sort of analog. It's not 1 or 0, which is sort of noise free. It's in between in this weird state. You end up introducing a load of noise, and that's the main challenge facing quantum computing at the moment. Accuracy, and the fact that the bigger the system gets. Like if you go from 100 qubits to 1 billion, there's going to be loads of noise that you're going to add into that system that you can't correct. So because you can't look at this thing, you can't sort of correct for noise the way you would do with a normal computer.
Okay.
So you just have to do it in one shot, and you have to make your noise low enough, or you have to do something like error correction, which is whole nother field in itself. So you have to do all this stuff, in one shot without looking at it. And that is the toughest. That's the reason that a 1 billion qubit quantum computer doesn't exist today.